I wrote these when I was doing like the region questions.
All right, hit me. Well, don't really hit me, but hit me.
So when they give you like a question about fusion and fission, about like they'll ask you like what the process is and they'll give you like an example. How are you like supposed to know?
Okay, that's a good question. Let me break out this thing so I can write.
I'm not gonna lie, I don't know anything about fusion or fission.
Well, that's a problem.
Is there like a lot of questions with it?
There could be. I mean, it's really a. You guys see what's up there?
The glare.
All right, Caroline, go let the light off with the glare. Okay. So fusion.
Good job, Caroline.
Okay. Fusion and fission are both artificial transmutations. Okay. Artificial means that the human race needs to facilitate it. I mean, it's not going to happen by itself. You're not going to be walking down the street and be like, oh, there's a fusion and fission reaction. That doesn't happen. Okay. Fusion reactions will always have hydrogens or heliums as the reactants. So it will look something like this. H plus H, or H plus He, or He plus He. Okay? Those are all going to be your fusion reactions. Now, what they turn into depends on whatever the numbers are that you have here. So if this is a 3/1 and this is a 1/1, then this would be a 4/2 He. Because 3 plus 1 is 4, 1 plus 1 is 2. Okay? So anytime you have fusion, you are going to look at the left side, and if there's only hydrogens and heliums there, that's a fusion reaction. Okay? Now a fission reaction is going to start with a uranium. Now, I don't know what number they're going to put here. I'm just putting 235. Plus a neutron.
Oh,
Okay.
This is like the alpha.
And then, nope. Well, this is the same unit as that. But with a fission reaction, what's going to happen is that uranium is going to break down into barium, krypton, and 3 more neutrons. That's what a fission reaction is going to look like.
And it's going to be only those elements.
It's always going to be uranium and a neutron. Okay? So these two will stay the same. I don't know what these numbers are going to be. It all depends. Remember that the numbers on the top left have to add up to whatever the numbers on the top right are. Okay? The bottom numbers are going to be the atomic numbers. So I know uranium's 92. Barium, I think, is 56. I think I'd have this memorized after 30 years of doing this, but I don't remember. Let's see. Barium is 56. And krypton is 36. Okay? 56 and 36 add up to 92. There are 3 zeros here. So 92 plus 0 is 92. 56, 36, and 3 zeros is also 92. So any numbers that you have on the bottom here have to add up. Any numbers on the bottom here have to add up. Then you do the top, 235 and 91. That adds up to 236. And then whatever these two numbers are have to add to 236. I have no idea what they're going to be. Let's make this 137. And then you can figure out what the krypton's going to be. Keep in mind that that 137 can change. It could be any number. This number and 3 ones, 137. So now I've got 140. I need to get to 236. So what's 236 minus 140? What is it?
96.
Yeah, it is 96.
Okay, so then that would go here. Okay? They would have to give you these numbers, or at least some of them, and have one that's missing, so you know what that number is going to be. When you have a fission reaction, it is a heavy nuclei plus a neutron, and it breaks into two smaller pieces. Fission means to split apart. Fusion means to come together. Any artificial transmutation, will always have two reactants. Two reactants. If we are talking about natural transmutation, that's what you were talking about before. All right, with a natural transmutation, you're going to have one reactant, and it is going to happen without the help of a human. It is naturally happening. So we can go to anything on table N. Okay, let's say carbon 14. Carbon 14 will be my reactant. It will give off a beta particle. What does a beta particle look like? You're going to find that on table O. Right there, beta particle. Looks like this, 0 over negative 1e, which is what I wrote there. Second word. And now I can figure out what goes here. Right? If I know there's a 14 here, that arrow's my equal sign, 0 plus 14. Carbon has an atomic number of 6. That's the bottom left number. This is going to be a 7.
Oh, okay. Yeah.
Be careful with that, right? I see that happen a lot. 7 plus negative 1 is 6, and 7 is atomic number, atomic number 7 is nitrogen. So make sure that your top numbers are equal to each other. So this side is equal to whatever's going on over here. And then this 6 is equal to whatever numbers are going on down here. Summed up. Okay? This is called beta decay. It's a natural because it has one reactant. You can do francium-220. Francium is atomic number 87. Getting that here. Okay. We look at table N. Francium-220 is going to give us, where the heck is it? An alpha particle. So that's going to be alpha decay. An alpha particle is helium nucleus. I'm getting that from table O. Alpha decay. See the symbol? Then we just do the same thing. 220 equals 4 plus 216. 87 equals 2 plus 85. We go back and we look at atomic number 85. And I see it's AT. And then you put AT here. Okay? Alpha decay, beta decay, positron emission. All three of those are natural transmutations. The word transmutation means to change. It is changing from whatever this starts as to whatever it ends as by giving off whatever particle it is. Beta particle, alpha particle, so on and so forth. Okay? What? Light work, right? Cops, whatever that is.
That means like I got it.
Got it. Oh, like I copy on a CB radio.
Just
Yeah.
one.
Like
That
10
second
four,
one
good
was
buddy.
alpha decay.
The second one was alpha decay. This is alpha because it's giving off an alpha particle. Okay? All right, hit me with the next one. Or did you have more?
Yeah.
So we went over natural and artificial transmutation, fission and fusion. Everybody good with that?
Yeah.
Okay, move on.
So
What's next?
fusion
Fusion means to fuse together, to come together. So two small things become one bigger.
Fusion was only with
Hydrogens and heliums.
And then
Fission, split apart. Division, fission, division. They're dividing into two smaller pieces.
how do we know which
What they're gonna
to use?
divide them into?
Like how do you know? Well, we have to choose like VA, but then they're gonna give
They're
us.
gonna give you this. There's a couple ways they ask this. Hold on one second, Alyssa. They're going to give you which of the following is an artificial transmutation. Then you're looking for it to have the numbers on top and bottom and have two reactants.
Well,
They will also give you something where one of these is missing. And you have to fill it in. Fill in the numbers just the way we did it. The top numbers have to be equal and the bottom numbers have to be equal. Okay? They're never going to ask you to memorize this. They're not going to ask you to write it out of, just write it down. They're not going to say, write down a fission reaction. That will never, ever, ever happen. They will give you a fission reaction with one thing missing. You're going to have to put that in. They will give you 4 choices and say which one is a fission reaction. They'll do that. But they will never ask you.
you watch this movie with a different phone.
I didn't watch that movie. I don't even know where that movie came from. Okay. All right, go. Hit me with the next topic. Oh, we go back to Regents.
So I got this one wrong.
Okay,
And-
what does it say?
Okay. What is the total number of moles of atoms present in 1 mole of Ca3? I don't know, it's a compound PO4 parentheses 2.
Okay. How many moles of atoms? What's another word for mole? Group. So if we change this to group, one group of this has how many groups of atoms in it? How many calciums do you have? 3. How many phosphorus do you have? How many oxygen? 8. That's 13 total. How many groups of atoms are in one group of the calcium phosphate? That's what they're asking. You don't see that, do you?
Wait, say it again.
Okay. If you look at that question, it says how many moles of atoms are in 1 mole of calcium phosphate, right? Isn't that what it said?
Yeah.
Okay. So let's change it to, let me write that. How many moles of atoms are in 1 mole of Ca3PO42? Okay? Now let's change these words. Mole to group. Mole to group. How many groups of atoms are in 1 group of this? If you have one group of this, how many groups of atoms do you have? Well, you have 3 calciums. That's 3 groups of calciums are in here. You've got 2 phosphorus, and you've got 8 oxygens, which gives us a total of 13 groups of atoms. The word mole is what's throwing you off. The only thing they're asking you is how many atoms are in 1 Ca3PO4. How's that? Better? Get rid of the word mole and just read it like that. Okay? All right, next. I know you have a list, so go.
Okay. Can you go over equilibrium shifts
I can.
with pressure?
I can. Let's go over all of them. You ready? In terms of Le Chatelier's principle, if you see something that says in terms of Le Chatelier's principle, they want you to say, does it shift to the left or does it shift to the right? That's what they're asking you for. Guys, Le Chatelier's principle says a system at equilibrium will shift, and by shift I mean shift to the left or shift to the right, to alleviate the stress. There were 3 stressors: pressure, temperature, and concentration. I don't know why I wrote pressure first, but I'm going to do pressure last. Boys, if you're going to talk, you got to leave. Okay? You want a pen? Okay. Let's say we have a reaction that's at equilibrium that has a double-headed arrow, and we've got ammonia. Okay? I'll make sure it's balanced. 2 N's, 3 hydrogens, or 6 hydrogens, 3 moles of hydrogen, and 6 hydrogens over here. All right, so now it's balanced. This is a gas, this is a gas, and this is a gas. That's the reaction we're working with right there. Okay? It is at equilibrium, which means what? What does equilibrium mean? The rate at which I'm going in the forward direction is equal to the rate at which I'm going in the reverse direction. Rate is equal. Concentration is constant. Rate is equal. Concentration is constant. Okay, so everything is going along swimmingly here. And now I've got a shift, or something is going to stress this system out. I'm going to add nitrogen. If I add nitrogen, the reaction is going to shift to the side opposite where I'm adding. So if I add nitrogen, the whole thing shifts to the right. If I add nitrogen, what's happening is there's more collisions between the nitrogen and the hydrogen. Remember collision theory?
Yep.
Okay? The more collisions, the faster the reaction is going to take place. If I add nitrogen, there's more collisions between these guys. It's going to turn into ammonia quicker than the ammonia is turning back into nitrogen and hydrogen. Eventually, it will reestablish equilibrium. However, when I stress a system out, there is a shift away from whatever you are adding. In this case, I add nitrogen, it shifts to the right. If I add hydrogen, it shifts to the right. If I add ammonia, it's going to shift to the left because the ammonia is over here. Do you understand what's happening?
Yep.
Boys, I don't know. Do you understand? I don't know where you're coming from. Jack, who's your friend back there?
Justin.
Justin, you understand, Justin? Are you just yesing me to death? If I add ammonia, which way does it shift? Hey, Brady. If I add ammonia, which way is it going to shift? Left. It shifts to the side opposite what you are adding. All right, so that's this one. That's concentration. Check. Whoops. Check. If I have the same equation and I know that it is exothermic, exothermic means heat is over here. If I add heat, which way will it shift? To the left. It's to the side opposite what you are adding. If I add heat, it shifts to the left. If I take heat out, it's going to shift to the right, because I'm going to try to replace what I am removing. Okay, so that takes care of temperature. Now comes the big one, right? The pressure one. Nowhere in this equation do you see the word pressure, so you don't know what side it's being added to. Got it? Okay. So what we have to do for pressure is we have to look at the number of gases we have on either side of the arrow. On this side of the arrow, we have 1 gas here and 3 gases here to give me a total of 4 moles of a gas. That's on the left side. On the right side, I only have 2 moles of a gas. See how much smaller it is? Okay? So the way I always say to think about this is, let's say you have a big, gigantic hose that's connecting these two, and I start putting pressure on the system. This is me, pressure, 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 pressure. When that pressure comes down and hits the balloons, it's going to hit this balloon first. And it's going to push the gas that way. you always push the gas to the side that has less gas until both balloons are going to be the same size. So pressure is the only one that's different in the sense that there is no pressure written up here. You have to actually look at the gases to figure out which direction it goes. Capiche? Go ahead, Jack.
How would you answer the question?
Okay. If I increase the pressure, which way will it shift? Left to right. It's gonna go to the right. If I decrease the pressure, it's gonna go to the left. If they say in terms of Le Chatelier's principle, your answer will be it shifts to the left or it shifts to the right. That's in terms of Le Chatelier's principle. So let's say they say in terms of Le Chatelier's principle, what will happen if the pressure on the system is increased? If the pressure on the system is increased, it will shift to the right. If the pressure on the system is decreased, it's going to shift to the left. Okay, let's see if, hold on a second. Let's see if we can. Maybe. I won't be able to. Here we go. I got it on my third try. Base your answers to questions 57 and 58 on the information below. Given the reaction at equilibrium, here's the reaction. 2NO2 plus 7H2, and they're both gases, at equilibrium with 2 ammonia gases and 4 water gases, and 1127 kilojoules of energy. On the diagram in your answer booklet, complete the potential energy diagram for the forward reaction. Be sure your drawing shows the activation energy and the potential energy of the products. Okay, and this was a 2-point question back in the day. All right, what does the potential energy diagram look like? This looks like it's locked. Hold on, what is happening here? I don't know either. It doesn't.
Josh, why are you black?
All right, hold on a second. Let's stop the camera. It's also on tape. So you have to go back and listen to me. It's for you. All right. So back to the question now that I got the camera working. On the diagram in your answer booklet, this is what it's going to look like. It's going to say potential energy. And it's going to say time. Okay? And it's going to ask you to draw the potential energy diagram for the forward reactions. Is this forward reaction endo or exothermic?
Exo.
Exo. So with an exothermic reaction, Caroline, for her,
Okay.
you're going to start high and you're going to end low.
Talk.
That is an exothermic potential energy diagram. If we had the heat, if this 1127 was on this side, it would be endothermic, yes? and it would have looked like this. Okay? This is an endothermic graph. This one is an exothermic graph. Heat or energy or that number or whatever is on the product side. Here, the energy would be on the reactant side. Example, A plus B plus heat yield AB. Here, we had AB yield A plus B plus heat. See how it is on the product side? And here it's on the reactant side? All right. This one that we were just looking at, the heat, which is right here, is on the product side. So because it's on the product side, the graph is exothermic. Then it says, be sure your drawing shows the activation energy and the potential energy of the products. Where is the activation energy on this graph?
Somewhere.
Right there. That's the activation energy. So A is activation energy. Where's the potential energy of the products? Bottom right, over here. That's the potential energy of the products. Welcome back. You have to go downstairs?
Oh, I give up.
I'll see you later. Okay? This is not what is asked in that question, but I'm going to go over the bits and pieces anyway. Over here, C is the potential energy of the reactants. Bless you. Okay, so that's those three. D, which is right here, is the potential energy of the activated complex. E, I'm running out of colors here. E, which is right here, is the activation energy of the reverse reaction. And then finally, I'll do it in red. Did I do blue already? Orange, here. This one right here in the middle, which I'm going to make F, is the delta H, or heat of reaction. That delta H, which is heat of reaction, is the potential energy of the products minus the potential energy of the reactants. Go ahead, Jack.
First, we have to know.
All of them.
So that's a box. Jerry, can you send me that? Yeah, I got you. I bet.
Okay, make sure I look good in that picture.
I didn't get you in it.
Ah, darn it.
So,
Yeah, go ahead.
ideal gases.
What?
Ideal gases.
Okay. Give me 1 second and we'll go over ideal gases. Jared.
I'm not done yet.
He did nothing.
Please, Miss Kaufman, we're not done.
Okay. He did nothing. You focus on your pretzel chips.
I'm almost done with that.
I'm sorry to hear that. Okay. The delta H, if the delta H is negative, it is exothermic. If the delta H is positive, like in the other graph, it's going to be endothermic.
It was a little hot up there.
Okay.
You just started looking at this.
I thought you were like trying to find a signal on your phone.
Oh. I'm sending people the picture I took.
All right, what I did forget to put on here, and I I say this every year and it doesn't happen, but I'm going to say it one more time. If they ask you to draw a catalyst,
Oh, it's the line across the.
it's the line that goes just below this curve. Make sure that you don't go anywhere near these two flat parts of the graph. Word to the chemistry people. Okay? Do not go below those two lines. This line and this line. Because if you do, it will be wrong. I don't care if you do it really close to the top here. Doesn't matter to me. But do not do this. Got it, Jack?
Where are the dots? The catalyst.
This is the catalyst.
Okay, actually to draw one, you put it in that area.
And the catalyst, what it does is it lowers the activation energy. In other words, if you're standing here and you want to get to B, you do not need to climb to the very top of the hill. You just have to take this little shortcut and go down to the other side.
Lowering the activation.
Mm-hmm. Yes, it lowers the activation energy. It also changes the potential energy of the activating complex, but they don't really ask that. They could potentially ask you what line it changes. In this case, it would change line D, it would change line A. It definitely does not change C, F, or B. Okay? All right, any other questions on this potential energy diagram?
Jared, take a new picture. The catalyst. Nah, I can't do all
You can
that.
take a picture, or it's on tape. You can go back and listen to me a million times. All right, Josh, you asked me about gas laws. All right, ideal gases. So let's flip over to gas laws just for a second. Actually, no, we're not doing that yet. Hold on, give me 1 second.
Okay.
So we did 57. We drew the potential energy diagram. That was here. We labeled the activation energy of the forward and the potential energy of the products. That's the activation energy of the forward and the potential energy of the products right here. We did not do number 58. Explain in terms of Le Chatelier's principle. And when you see explain in terms of Le Chatelier's principle, what are you going to answer?
Left to right.
Left to shift to the right. Why the concentration of ammonia decreases when the temperature of the system increases. If I increase the temperature, which way is it going to shift?
Left.
Done. That's the answer. It shifts to the left. That is why ammonia decreases. Because everything that's on the right gets pushed to the left. Okay? You understand?
Yeah.
If it says in terms of Le Chatelier's principle, the answer will be it shifts to the left or it shifts to the right. All right. Ideal gases. Gas laws. Okay. Gases behave in a certain way. The kinetic molecular theory says.
Can't see it.
All right, hold on. Where am I? There we are.
It's really close to my face. I wouldn't answer that.
It says gases travel in continuous straight lines. That means if I'm a gas particle, I am going to travel forever in a straight line. Now, does that really happen? No. Eventually, it's going to hit something. Okay? When it does hit something, it bounces back. And those collisions with things are perfectly elastic collisions. Yep. Pen? Do you care if it's red? Or maybe green?
I'll take the red one.
Yeah, because this, I don't know what it is. The green one. Alright. Like,
It's Christmas.
there you go. You have choices now. Are perfectly elastic collisions which means when they finally do hit something, they're not going to lose any energy. That doesn't happen either. Okay. They have small volume compared to the size. In other words, if I have a container here and I've got gas particles in there, the volume of the gases, if I shrunk all these little dots down, that the volume of those gas particles is very small compared to the volume of the container that it takes up. Okay? So gases behave in certain ways. We can manipulate a gas by adjusting its temperature and its pressure. If I increase the temperature on a gas, the gas particles are going to spread out. They're going to start moving faster. They're going to hit the inside walls of the container, okay, with more speed, and they're going to push that container out. Or if the container doesn't move, the pressure is going to increase in it. So if I heat up a gas, the gas particles are going to spread out, and they're going to behave more like what we would expect a gas to behave like. It would be a perfect gas. The further the gas particles are away from each other, the more likely they're going to travel in continuous straight lines without hitting anything, because there's less things for them to hit. Does that make sense? Kind of, sort of? Anyway, bottom line. We want gases to behave ideally, perfectly. Okay? When those gases are behaving perfectly, we have to have very high temperatures and very low pressures. So ideal gases, which is what Josh was asking me about, gases, there are no ideal gases. There are no perfect gases out there. No gas does these things. Can we get them to behave more like an ideal gas? Yes. We can do that with low pressure and temperature high.
So what do you mean temperature high? To make a high temperature?
Yeah, like heat it up. Heat that sucker up. And when I heat it up, they expand and they get further away from each other, which means they're less likely to hit each other. They're less likely to hit anything else. Okay? All right.
Isn't that like flight?
Yes, that's flight.
Wait, what? It's flight. It's flight.
Pressure low.
Oh.
Look.
Looking.
Pressure low. Ideal gas.
High temperature.
High temperature.
Okay.
So if we want a gas to behave like an ideal gas, we need to get the pressure to be low and the temperature to get high. Pressure low, high temperature. Flight.
Light, could never learn that.
Yes, we did.
How would that come up in a
Well, let's take a look and see what we can find. Okay. So,
Wait, wait, are you recording?
yeah, I'm recording. Actually, let me show you. Which statement describes the particles of a perfect gas, an ideal gas, based on kinetic molecular theory? The volume of the particles is considered negligible. Negligible means zero. Right here,
Wait, the next.
the volume of a gas is small, negligible, zero. Negligible means zero. Okay? Compared to the size of its container. In an ideal gas, is the volume of the gas considered negligible?
Yeah.
Yes, it is. So this is my answer. The volume of the particles is considered negligible. The force of attraction between particles is strong. Are these gas particles attracted to each other? No, they want to spread out as far apart from one another as possible. Are they packed in a regular repeating pattern? Now, what types of particles are packed in a regular repeating pattern?
Wait.
Solids. And the particles are separated by small distances. Are these particles separated with small distances? No, they are large distances. So that's one. All right. Here's another example. There was 2 ideal gas questions on this Regents. I just picked by random, June of 19. State a change in temperature and a change in pressure of the carbon dioxide that would cause it to behave more like an ideal gas. How do we get a gas to behave more like an ideal gas?
Low
High
pressure. Low pressure.
High temperature.
High temperature. That's the answer.
Yeah.
That's how they're going to ask you.
Okay.
Okay? If we want a gas to become ideal or perfect, we want it to have low pressure, high temperature. And if it has those things, the gas particle is going to be really far apart. That means they're going to travel in straight lines. They're not going to be attracted to each other. They're going to not lose as much energy because they are far apart from anything that's going to slow them down.
Wait, what do you mean travel in a straight line? It's like, they go in a straight line?
Alyssa's like, you got this? It's like, go. Forever, never, 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 never.
When we're done with this, I have a question about a whole different unit.
All right, can you hold it 1 second? There's one more thing I need to say. The other thing one more thing for gas, ideal gases, okay? When we have an ideal gas, there are two gases on the periodic table that behave like ideal gases. They are hydrogen and helium because they are small. Small gases will also behave like an ideal gas because you can't see. All I wrote was hydrogen and helium. They will behave like an ideal gas because they're so small that they can fit through very small spaces. So if you think of it like this, if you've ever kept a bottle of seltzer water or soda, and after a couple of, I don't know if you keep soda that long, but couple weeks, couple months, whatever, it's not as fizzy.
What?
It's flat. And the reason is, even though it's closed, the gas can still fit through the little microscopic holes in the plastic of that container. The smaller the gas is, the more it can fit through the holes. You with me?
Yeah.
Boys in the back, if you don't want to listen, it's fine, you can leave.
I was caught when Alyssa had a soda that had a name on it.
I got it when I was like 5. And I just threw it out.
A soda?
Yeah.
It had her name. It was like,
And it was flat, wasn't it?
It was like squishy.
Yes. Squishy because there was no more gas in it.
it was a biohazard. It's called. I think for 10 years.
The soda will last forever.
Not that one.
It's
That's
only
scary.
sugar water.
Wait, if it's
With gas laws is the gas law formula.
it's on the reference table.
It is on the back of your reference table.
Wait, don't say it. I'm gonna say it.
Okay. Go ahead.
I found it.
Wait, is it the P1 V1 over T1 equals P2 V2 over T2?
That's it.
That sounds like a good.
Okay. P stands for pressure. Once again, boys, I do not need to be doing this. P stands for pressure. You can find standard pressure on table B. I think it's B, right? It's A or B. It's on the front of your reference table. A, exactly what I said. A, standard pressure, 101.3 kilopascals or 1 atmosphere. Those are your standard pressures.
Wait, so which one do I pick?
Depending on what the other one they gave you in the problem is going to be. We'll do a couple of these as examples. I'll show you. Okay? They also give you standard temperature. What's standard temperature? 273 Kelvin or 0 degrees Celsius. In a gas law formula, Caroline,
Yeah.
you never use Celsius.
Okay.
Only K.
Okay.
This one.
It can't be 0.
Can't be 0 in the denominator. All right, let's find a gas law problem. What's that? Oh, there was? Oh, here it is. 59. Good eye. Okay. It says a 200 milliliter sample of carbon dioxide. Let's draw a picture. Let's say it's the day of the Regents and I'm just standing here. Draw a picture. 200 milliliters. 200 milliliters, that's a volume.
Your screen's frozen.
My screen is frozen. Okay? 200 milliliter sample, that's right here. I drew a picture. There's a balloon. It has a volume of 200 milliliters. It's placed in a sealed, rigid cylinder. Well, it's not a balloon, so let's stop that. I didn't read it. Sealed, rigid cylinder, 200 milliliters. That means that this thing does not change in volume. It stays 200 milliliters. Wasn't a balloon. Balloons expand.
Air.
With a movable piston at 296 Kelvin, so this thing is 296 Kelvin. That's its temperature, and 101.3 kilopascals.
Wait, what's the piston?
A piston is like, let's say you have a tube, and it has like a stopper on the top, and it goes up and down. That's a piston. Look, I'll show you. Of course, I can't find a good picture to show you. These are car pistons.
I don't do cars.
I'm not asking you to do cars.
I
All
found
right,
my
here's an example. All right. You see this thing, this red line right here, Caroline?
Yeah.
You see how it's down low, and then it went up,
Yeah.
and then it's up, and then it's down? This is a movable piston. It goes up and down. Okay? All right. Determine the volume of this sample of carbon dioxide if the temperature and pressure are changed to 336 Kelvin. So we're going to change this to 336 Kelvin and 152 kilopascals. This didn't change size. Okay? What's the new volume? What? Can't see it. Okay? So let's write the formula. P1 V1 over T1 equals P2 V2 over T2. The first volume was 200 milliliters. The first pressure was 101.3 kilopascals. And the temperature was 296. The second pressure was 152 kilopascals. The new volume, we don't know. And the new temperature was 336 Kelvin. Now, Caroline's favorite pastime activity. Actually, you know what? Let's just move this over just a little bit.
I think it's favorite.
It is your favorite. Okay? Let's cross multiply. 101.3 times 200 times 336.
Let Caroline do this.
Okay.
Okay. So. Let's see.
I have no idea what the answer is, so go ahead and figure it out. Oh, you can round. It doesn't say you have to.
Caroline got it right. Wait, hold on.
How do we know Caroline got it right?
Because I watched her do it. Wait, Miss Crawford, I didn't finish it. Oh, wait, also, so I do. 9 December. And then you divide big number by that. Wait, where's the extra? Right next to that, okay. Deduct this.
All right, I gotta find a calculator. 101.3 times 200 times 336 divided by 296 divided by 150.
That seems right.
151.3?
Oh my god, I got it right, Miss Crawford. Yay!
Milliliters. Is that what you got?
I have 1.
That's what I got, 151.3. You go, girl. You didn't get that?
No, I got that.
Or is that what that grunting is for?
It's called getting it right.
Oh, that was a getting it right sound. Not of the same one. We got other things to do. All right. State in terms of both frequency. Sorry, I got to turn the tape back on. If you have a gas flow problem and it says at STP, let's say they didn't give you the new pressure and temperature. Let's say these two weren't given to you in the problem. It said at STP. So if you have this and it went to STP, you get the STP from your table A. So be careful with that. All right. Something else I was just about to tell you. Oh, pumpkins. I can't remember.
Pumpkins.
I like pumpkins. Anyway, that's neither here nor there. All right, number 60. State in terms of both frequency and force of collisions what would result from decreasing the temperature of the original sample of carbon dioxide at constant volume. So what would happen to the frequency and force of collisions if you decrease the temperature? What would decrease? The frequency of collisions would decrease and the force that they would be exerting would decrease. Okay? Because they're not going as quickly. Compare the mass of the original 200 milliliter sample of carbon dioxide to the mass of the carbon dioxide sample when the cylinder is adjusted to the volume of 100 milliliters. No, it's not. It's easy. Mass is grams, right? Yes, no?
Yeah.
Okay. If you took me and I weighed 100 grams, right? And you shoved me into a suitcase, would I still weigh 100 grams?
Yeah.
Yeah. Okay? Compare the grams of the original 200 milliliter sample to the grams of carbon dioxide when it is in 100 milliliter sample.
It's the same.
It's the same. The mass did not change. What changed was how big a space it takes up. You understand?
Yeah.
Okay, that's that question right there. Oh, look at this.
Oh,
We just did this, didn't we? Let's do them just because we can. Are you leaving us?
Yeah, we're going to some beaches.
Oh, yeah, he's so much better.
I actually did good on Friday.
Okay. Cobalt 60 is an artificial isotope of cobalt 59. The incomplete equation for the decay of cobalt 60, including beta and gamma emissions, is shown below. What is that, X? Jared.
He's really making like.
Jared. What is X? Why my thing is a little bit off? Okay. What number goes up here?
60.
60. And the bottom is going to be 28. What element is 28?
Oh.
And
I.
Good.
Alright.
So 60 over 28 Ni. That's your answer for one of these.
Wait, what's the squiggly line?
This is a gamma particle. It's on table O. All right. What's the matter? You good?
Because look. Number plus 0 plus 0, 60 plus 6. And the right side has to be
60 equals 60
Yeah.
plus 0 plus 0. 27 equals 28 plus negative 1 plus 0.
So 28 plus. Okay.
28 plus a negative 1.
Would be 20. So 28. Wait.
28 plus negative 1 equals 27.
Okay.
This side of the equation is got to be equal to this side of the equation. That was a poor choice of color. Okay?
Okay.
All right, we did that in the beginning of today's review. I'm sure that question's going to come up. Explain in both terms of both protons and neutrons why cobalt 59 and cobalt 60 are isotopes. Josh. Perfect. The definition of an isotope is the same number of protons, different numbers of neutrons.
Yes.
Okay, that's the answer to that question. In terms of both protons and neutrons, make sure that you say protons stay the same, neutrons change. All right, compare the penetrating power, and I didn't talk about this yet today, of a beta and a gamma emission.
Yeah.
Gamma has the greatest penetrating power,
Yeah.
and beta is less penetrating power.
Wait.
Gamma has the greatest penetrating powers, alpha has the least, and beta's in between. All right, 64 is the one we just answered. It's the what is the X? Complete the nuclear equation in your answer booklet for cobalt 60. Based on table N, determine the total time required for 80-gram sample. 80 grams to decay until only 10 grams remain. If I start at 80 grams, after one half-life goes by, how many am I going to have left? 40. 40. After another half-life goes by, 20. And then after a third, I have 10. So how long does it take to go from 80 to 10? Well, look up how long cobalt 60 takes. Is it how many? 15 what? Years, seconds, months? Cobalt 60.
15 years.
5.27 years.
So 5 that times 3.
Cobalt 60 takes 5.271 years. So each one of these is 5.271. I've got to do that 3 times. And so it's 15 point. All right. 5.271. 15.813.
Yeah.
You didn't do that yet, so don't tell me yeah.
I did it.
Am I right?
Caroline did it.
Caroline, you are the best math rock star.
I know, it was Kaufman.
I could do that too. I just don't.
I'm not that proud. Yeah, you are.
This is for a few minutes. First of all, you're going to find your acids, your common acids on table K. You're going to find your common bases on table L. Table K, when you look at it, you're going to see most of your acids start with an H. HCl, H2SO4, H3PO4. Okay? Arrhenius acids. The definition, Arrhenius is just a person. Arrhenius acids, the definition is they donate or give away an H plus ion in solution. Let me write that down for you. Arrhenius. They give away H plus ion in solution. H plus ion can also be written as an H3O plus or a hydronium ion. An Arrhenius base gives away an OH ion in solution. The OH ion is called a hydroxide ion. And these hydronium and hydroxide are listed on your polyatomic ion table E. When you have an acid, it will dissociate. That means break apart into H plus and whatever the negative ion is. Every once in a while on a reagent, they'll say, what's the positive ion in this compound? You have to be able to break apart or dissociate an ionic compound or an acid or a base. That means break it into its positive and its negative. Arrhenius bases will dissociate into a metal ion and a hydroxide. That's how you know you're dealing with a base. It must be a metal and an OH.
Did you eat breakfast today? Do you have breakfast?
No, I had a cake pop.
We're picking
Delicious. Couldn't have eaten it. Should have had an egg.
I had strawberries.
Yep.
Like sometimes if I give you an equation, I'll ask which one's done with H plus and something.
Sure. Okay. If you have an acid, it's going to give off an H plus. How do you know it's an acid? It's going to start with an H and end with some sort of polyatomic ion or a negative ion. Okay? If you have a base, it's going to start with a metal and end with an OH. So what you're saying is they're going to give you something that says, which of the following donates an H plus ion in solution? And they might have something like this, sodium chloride. They might have H3PO4. They might have magnesium hydroxide. And they might have ammonia. Okay? Which of the following will donate a hydrogen ion in solution? If it's going to donate a hydrogen ion solution, also called a hydronium ion, you're looking for an acid. And the acid is going to start with an H. Okay? That's how I know. Also, look at your table K to help you figure out which ones are acids. If they asked you which of the following would donate a hydroxide ion as the only negative ion in solution, this one would give off an OH ion as the only negative ion in solution. Okay? Bases give off OHs, acids give off H's, according to the Arrhenius definition. If you have an alternate acid base, alternate acid base, then acids are going to donate an H plus exactly the same way that these guys did. Nothing changed. They gave away an H plus. Donate means give away. They just use donate sometimes to make it sound like they're smart. Okay? They give away an H plus or an H3O plus. Okay? Nothing has changed yet. Bases, however, accept an H plus. So an Arrhenius base gives away an OH. An alternate base accepts an H. Not an OH, accepts an H. Okay? So if you have ammonia, let's say, NH3, plus water, which actually I'm going to write as HOH. Okay? That doesn't have any OHs to give away. So it cannot be an Arrhenius base. So it has to accept an H from this water. When this H comes over here, it makes NH4 plus. That H plus, which is right here, goes over here, brings with it its H plus, NH3 plus H plus, gives you NH4 plus, and it leaves an OH behind. So you still get the OHs, but you got them by dragging an H plus off of the water. Stop with the conversations. Yes, Jared, you. I love you dearly, but stop talking. Okay? There are some bases that do not give off OHs. They accept H pluses. They take H pluses away from something else, mainly the water, so that they can have the OHs dangling out in the solution. Okay? When you have an Arrhenius base, you get the OHs because this guy gave them away. But if you don't have any to give away, you can take H pluses and still have the same effect. Okay? Ammonia is the only non-Arrhenius base. This is an alternate acid-base reaction right here. Because this, go away, I want an eraser. This ammonia is accepting an H+. This is a base. It's paired with this guy, which is going to be an acid. How do I know they're pairs? They differ by one hydrogen. The one with more hydrogens is going to be the acid. The one with less hydrogens is going to be the base. This is also a pair. Out of this pair, this one has more hydrogen, so it's going to be the acid. Whoops. And this one is going to be the base. These are called conjugate acid-base pairs. Don't spend an enormous amount of time on this. Okay? Just know the definition. If you have an acid, you give away an H+, no matter what kind of acid you are. If you are a base, you either give off an OH or you accept an H+. Those are your definitions. Okay? All right, let's talk about the pH scale for a second. 0, 14, 7 being neutral. If you are lower than 7, between 0 and 7, you are an acid. If you are above 7, from 7 to 14, you are a base. Down here, where you're really close to 0, you have the most H pluses and the least OHs. Up here, you have the least H pluses and the most OH minuses. One, 2, 3, 4, 5, 6. Not drawn to scale. 7, 8, 9, 10, 11, 12, 13, 14. Let's say that's good. What? That's good news.
I don't.
Okay?
That's not good.
Every time I move a number, this is on a lot of Regents exams. Every time I move a number, let's say I'm going this way, from a pH of 1 to a pH of 2, I change by a factor of 10. Okay? So 1 has more H pluses, 10 times more H pluses than 2. Because 1 is closer to down here where you have the most H pluses. 1 is going to have 10 times less OHs than 2. You get more H pluses, also known as hydroniums. I'm going to say that one more time because they like to use that word. Okay, you have more hydroniums down here. Every number is a factor of 10. So if I go from 1 to 3, let's say I go from 1 to 3, I have 100 times less H pluses or 100 times less hydroniums because I went this way. If I go this way, I have 100 times more hydroniums. You understand? They love to ask that question. Also, with a pH of 1, 1.0, Let me erase that for a second. It's too fat of a pen. 1.0 times 10 to the negative 1. 2. 1.0 times 10 to the negative 2. 1.0 times 10 to the negative 3. These numbers, these exponents are the pH numbers. Okay, I saw that on the Regents too.
Wasn't there like problems that we used to solve to find like the pH or something?
There's an equation, they won't ask you it. Okay? They will do this. 0.0001. Hydrogen ions. What is the pH? That they can do to you. Josh? You ready?
Going backwards.
Say that again, going backwards?
What's that?
If you mean going backwards in pH number? If I go from 2 to 1, my hydrogen ion concentration goes up by a factor of 10. If I go from 1 to 2, my hydronium goes down by a factor of 10. Every jump in number is a factor of 10. Okay, let's go back to this. What would this pH be? No multiplying anything. How many decimal places do you have here? 4. pH of 4. 0.00000001.
5, 2, 3, 4, 5, 6, 7. pH of 7. I remember this. Okay. No.
1, 2, 3, 4, 5, 6, 7, 8. Okay, how many decimal places? That's your pH. Got it?
So ever how many decimal points places are?
Yeah, because this would be 1 times 10 to the negative 8, which is this number. That's the pH. Because I'm going that way. This is 1 times 10 to the negative 4, because I'm going that way. All right, measuring concentration. Yeah. Aquifer? I do, but not here. I think I just gave it to my husband the other day. All right, concentration. Molarity, moles over liters, or parts per million. Parts per million equals grams of solute over grams of solution. Solution I'm abbreviating SOLN times a million. A million has 6 zeros. Molarity or parts per million. Let's do a parts per million question. Based on table F, write the that's not a parts per million question. Sorry, I read the wrong one. Show a numerical setup for calculating the parts per million of sodium ions in a 500 gram sample of the bottled water. Okay, what's the grams of solute? Yep.
5.0033.
500 of solute.
Solute. Solute is the substance that is being dissolved.
Oh, that's what I said. 0.00.
That's the grams of solute. What's the grams of solution?
500.0033.
No, you don't have to add them together because it says the bottled water. The bottled water is the solution. The sodium ions are already in it. Times a million. If they said just in water, then it would be add them together. But because they said the bottled water, then you knew the bottled water already had this stuff in it. Now we multiply it by 1,000,000. That's going to give you parts per million.
That's easy. I like doing it.
It's easy for me. I don't know about you.
I like doing it.
I got 6.6. Is that what we got? Oh, you can't see a thing that I'm doing. I took the grams of solute, which I got from here, over the grams of the solution, which is the bottled water, and I multiplied it by 1,000,000. Go ahead.
Why did you pick up more, Grace?
Because concentration can be either measured in molarity or parts per million. Depends on what they're asking you to do. If they ask you for the concentration in molarity, then you do moles per liter. If they ask you for the concentration in parts per million, you do grams over grams of solution.
How do you know when to combine like the solute?
Okay? Well, you have to know what a solution is. A solution is both of them together. In this case, it said bottled water. They didn't say distilled water. It didn't say pure water. It didn't even say in water. It said in the bottled water. The bottled water is the solution. Ions in 500 grams of bottled water. Those ions are already in that 500 grams of bottled water. That's the solution. If they said you had 0.0033 grams of sodium ions in 500 grams of water, then that wouldn't be the solution. It would be the solvent. The water would be the solvent. Do you see the difference? If they said, here's salt, and here's 500 grams of water. 3 grams of salt, sodium ions, in 500 grams of water. This is the salt, this is the solution, the solvent. The solvent is what it is being dissolved in. Are you done with your review?
No one likes me, so they don't come to my room.
You could take over for me if you want.
How do I push these grades?
Mr. McGregor came in. So we've got 3 grams, just going back. The solution is both of these added together. But the bottled water in this particular example is already a solution. Okay? If they said it was dissolved in water, 500 grams of water, then you would have to add them together. All right, let's do the sig figs question for those of you who are going for the 100.
Oh, yeah.
State the number of sig figs used to express the mass of hydrogen carbonate ions. Here's hydrogen carbonate ions. How many sig figs are in that number? 3. Okay? Zeros don't count. Zeros in the beginning don't count.
Isn't that a month's investment?
I'm just gonna keep
I
talking.
know it's yours.
Oh, you're bad.
This 0 doesn't count because it's before. No, it has nothing to do with the decimal. It's before the first non-significant digit, which is the 1. There are no sandwich zeros, and there is a 0 over here. This 0 does count because there's a decimal point.
So, 3 sig figs.
It has 3 sig figs. How many sig figs does this sucker have?
3.
No. 2.
I hate these.
How many sig figs does this guy have?
2.
How many does this have?
2.
2. This has 2. Okay.
This one has 2 as well.
This one has 2, and this one has 3. Because they asked about this one, the answer is 3.
If they put 0.18 instead of 0.180, would it be 2?
What?
Yeah, he says if they put 0.18, let's say they did 0.18, then it would be 2 sig figs. Okay. I just did that one. Based on table F, write the formula for the ion in the bottled water that would form the least soluble compound when combined with a sulfate ion. So let's break out table F. I'm gonna do it up here.
But I passed it up in this.
Find table F.
Wait, I'm going.
Let's find the sulfate ion. Which ion would form the least soluble compound?
Wait.
Here's sulfate.
Yeah.
Sulfates are soluble, hold on, except with silver, calcium, strontium, barium, or lead. Which one would have the least soluble?
Wait.
The least soluble?
When combined.
Sulfate.
So yeah.
So yeah, calcium.
Yeah, it's the one that makes it not solid.
It's the only one that makes it non-soluble.
What happens if there were two on
There's
there?
not going to be, it's a regents.
Okay.
Okay? The least soluble is the only one that's insoluble is this calcium because sulfates are soluble except when they're with calcium. Alright, I'm clicking the wrong buttons here. Compare the radius of a magnesium ion to the radius of a magnesium atom. The magnesium atom is bigger because the magnesium ion lost 2 electrons. They didn't ask you why, they just said to compare them. But the magnesium plus 2 lost 2 electrons. So it lost a shell. If it loses a shell, it is going to be smaller than the magnesium atom. Oh, yay.
Oh, no, not yet.
Organic.
Yay!
All right.
Let's get going.
Ethyl ethanoate. Stop. What is ethyl ethanoate? What class of compounds does ethyl ethanoate come from? It's an ester.
Wait, how do you know that?
Look at the name. Look what it ends in. 08.
Oh,
Find on table R. You can't Google it.
can't. Okay, I found people are.
Oh, table R. Find the one that ends in an 08.
Esther.
Right. So this is an ester that we're dealing with. Is used as a solvent for varnishes and in manufacture of artificial leather. Again, remember, they're going to talk about things I've never talked about. Who cares? We know it's an ester. The formula represents a molecule of ethyl ethanoate. Identify the element in ethyl ethanoate that makes it an organic compound. Carbon. Carbon makes anything an organic compound.
Every single time. Every single time.
For organic.
Yeah, every time. See? Organic every single time.
Did that have anything to do with varnishes and
Nope,
solvents
nope,
and
nope,
esters? Nope. Okay, 75. Go for a long walk.
What?
Go.
Okay.
Take the long road.
Okay. We want to write the empirical formula. First, before we write the empirical formula, we want to write the molecular formula. Because the empirical formula is the lowest whole number ratio. So, how many carbons are in here? 4. How many hydrogens?
8.
How many oxygens? Uh-oh, I lost my page.
Oxygen?
Oh.
Yeah.
2. This is the molecular formula.
Okay.
Molecular formulas tell us how many exact number of atoms are in the compound. How do I make that empirical?
C8.
Write everything by 2.
C2.
Wait, so the molecular tells the exact number of atoms?
Exact number of atoms. The empirical tells us the lowest whole number ratio.
Wait, so what happens if some of them can't be divided by not divide, like, do I just add ones?
Then that one is the empirical formula.
Okay.
That's the molecular right here. If they ask you for molecular, you leave it exactly like that.
Okay.
If they ask you for empirical, you reduce it to the lowest whole number ratio.
Wait, so what would happen if, like, the H was a 7? But
If it was C4H7O2,
can I still divide it all?
you can't.
So that
So
would be
that would be empirical as well. It would be molecular and empirical.
no.
Okay? So empirical is always the lowest whole number ratio, no matter how you get it there.
Okay.
Molecular means I counted them and that's the exact number that I have. Write the name of the class of organic compounds to which this compound belongs.
Ester.
It's an ester.
Yeah.
Determine the number of electrons shared in the bond between the hydrogen and a carbon in this molecule. How many electrons are shared here between the carbon and the hydrogen? 2. If there was a double bond, then it would be 4. If it was a triple bond, there would be 6 electrons being shared. Right? So if you have a carbon to a hydrogen, that's a single covalent bond, 2 electrons. If you have a double covalent bond, that would be 4 electrons. If you have a triple covalent bond, that would be 6 electrons. Oh, baby.
Oh, I know.
Start at the anode. Electrons are lost there. Travel the wire.
Yeah, 78
and
is
go load
ions
on fire.
Well,
Okay, 78, nobody should be missing. Ions flow. Write a balanced equation for the half reaction that occurs at the magnesium electrode. Magnesium. Is the magnesium being oxidized or reduced? 2 ways to tell. You could either look at the reference table, and if you find magnesium, it would be reference table J, in case you didn't know. You could find magnesium and silver, so magnesium's here, you can't see. Magnesium is here, and silver is here. Magnesium is above silver, so magnesium is oxidized and silver is reduced. Or, you could just look at this equation, which they gave you, and it shows that magnesium is going from 0 charge to a +2, which means it's Leo, which means it's oxidized. So magnesium is being oxidized. So let's write the half reaction for the magnesium electrode. If it is being oxidized, it's Leo. That means its oxidation number needs to be going up. It's starting at 0 and it's going to magnesium +2. How many electrons being lost? 2. What side do they go on? What? On the right side. 2 electrons being lost. That's the oxidation half reaction. You're going to have to write one of those. Okay? Let's write the reduction half reaction even though they didn't ask for it. The reduction is the silver. You've got 2 Ag pluses plus 2 electrons becoming Ag0. That's the reduction half reaction. I'm not going anywhere. Can I do it again? All right, look. You see this 2 Ag plus?
Yeah.
All right, I'm going to write that down. 2 Ag plus. Okay, see it? Now, there's an arrow.
Yeah.
And it went to 2 Ag zeros. You see them over there?
Yeah.
So I'm going to write 2 Ag zeros. Okay. We are gaining electrons now. How many electrons are we gaining?
2.
2. What side do they go on? I didn't leave myself enough room.
On the left side.
They go on the left side, plus 2 electrons. I do that one. Explain in terms of electrical energy how electrolysis differs from the voltaic reaction. What do you know about electrolysis? What?
Battery.
It requires a battery. So explain in terms of electrical energy. You need to apply electrical energy through a battery in order for the reaction to take place in an electrolytic cell.
Did you say like in the electrolytic cell goes from electrical energy to chemical energy?
Yep.
Wait,
You take electrical energy and you make chemical reaction.
Wait, so what's voltaic?
A voltaic is a battery. It makes electricity. This one up here is making electricity.
So it's chemical to electrical.
This one is chemical. The one that you're looking at is chemical to electrical.
And
The
then-
one that has one cup,
Yes.
that one you need to put a battery on it. It is taking electrical and making or forcing a chemical reaction to take place. The battery is making a reaction take place. Without that battery there, nothing would happen. It is not spontaneous.
And then voltaic is fun.
Voltaic is spontaneous. That's this one. Voltaic is spontaneous. Electrolytic is not spontaneous. All right, we're almost done with this regents, even though I started in the middle. In a lab, a hydrochloric acid solution with a pH of 2 is used to determine the molarity of a KOH solution. A 7.5 milliliter sample of KOH is exactly neutralized. As soon as you see the word neutralized, what are you going to do? What formula? Titration. Okay, that's MAVA. We're probably going to need that MAVA formula somewhere down here. I don't know which one yet because I haven't read it. All right. A 7.5 milliliter sample of the KOH is exactly neutralized by 15 milliliters of 0.01. You see how they're connected with the word of?
Of.
That means they're going together on one side of the MAVA formula. During the lab activity, appropriate safety equipment is used and safety procedures are followed. Determine the pH of a solution that is 10 times less acidic than hydrochloric acid. Well, right now it's got a pH of 2. Less acidic, which direction am I moving? Which way am I going if I'm becoming less acid? To the right. So if I started at 2 and I want 10 times less acidic, you become a pH of 3. If they had said you are 10 times more acidic, then you would have been a pH of 1. Okay? All right, state the color of the indicator bromocresol green if it is added to a sample of KOH. Is KOH an acid or a base? It is a base. And so its pH is going to be higher than 7. Doesn't matter what that number is, it's higher than 7. What color will bromocresol green be when the pH is higher than 7? What color? Blue. You understand?
Yeah.
If they had said, what color would it be if it was a pH of 2, then it would be yellow. If they had said, what color would it be with a pH of 4.5,
Green.
it would be green.
Wanna know how I got that?
Does yellow and blue make
Green.
green?
Yeah. Good shit, Joe. You're mad smart, Smokey.
I am mad smart. So they pay me the big bucks. All right. Complete the equation in your answer booklet by writing the chemical formula for each product. This is what the formula would look like in your answer booklet. Let me just go to a clean page. Hold on. Okay. They would have HCl. Come on. HCl and KOH and they're gonna have two blanks. This is what it would look like. Complete that in your answer booklet. What two things go here? Say it again. HOH
ACL.
and KCl. Make sure when you write your formulas, you put your charges in and you cross them down. K is a +1, Cl is a -1, so it's nice and easy in this case, but it doesn't always have to be. All right. Show a numerical setup for calculating the molarity of the KOH. What formula are you using here? What? No. No. You told me in the beginning of this whole Megillah
Titration.
what formula you need to use. They asked for molarity. What formula am I using? Titration. Because molarity is in the titration formula. All right. What is the molarity of the KOH solution when you have 7.5 milliliters of KOH? That's the base. 7.5 milliliters neutralized by 15 milliliters of a 0.01 molar solution. That's what it looks like.
Wait, what? Let's just do that.
You have 7.5 milliliters of KOH. Milliliters is volume. So KOH is my base. My volume of my base is 7.5. I am looking for the molarity of my base, which is the molarity of my base. That's my X. Hold on a second. I didn't get that far yet, Hot Rod. Put on the brakes. Okay? It is exactly neutralized by 15 milliliters of 0.01 HCl. 15 milliliters is the volume of my acid. HCl is my acid. And 0.01 is the molarity of my base. See it?
Yeah.
You also see that these two numbers are connected with of.
So they're together.
They go together. Even if you didn't know which one was the acid and which one was the base, you knew those two numbers had to go on the same side of the equation. Right? And then you can do the math if you want, but it doesn't ask you to do the math. It says, show a numerical setup. So this is the numerical setup. All right. Explain in terms of aqueous ions why the 15 milliliters of the 1.0 molar hydrochloric acid solution is a better conductor of electricity than 15 milliliters of a 0.01 molar hydrochloric acid solution. Why is a 1 molar hydrochloric acid solution, because the 15 milliliters doesn't matter, it's the same, right? Why is a 1 molar better than a 0.01 molar?
Because
More what?
more HCl.
What does it say in terms of aqueous ions? There's more aqueous ions in which one?
The whole molar.
They're both HCl.
Okay, 0.01.
There's more in 0.01 than 1?
No.
No, because one's a whole one. Like that was done.
If you have something that is 1 molar and 0.01 molar, write it out. You got 15 milliliters and 15 milliliters. I know you can't see. Hold on. You got 15 milliliters of 1 molar and you've got 15 milliliters of 0.01 molar. Which one has more ions in it? Okay. So now answer the question. Explain in terms of ions why 15 milliliters of 1 molar is better electrical conductor than 15 milliliters of 0.01 molar. What has more? Which one has more? You can't say it. I don't know what it means. So you would say 1.0 molar
Is
has more what?
aqueous ions.
Has more aqueous ions than 0.01 molar.
That's right.
You can't use the word it. We don't know what it means when we're grading these things. All right. Any questions? Go ahead. I'm listening.
I still don't get it.
You don't get this.
No, I didn't get that to what you did before, like how you found out which one was more, like more aqueous ions.
Okay. So 1 molar means you have 1 mole for every liter.
Okay.
0.01 mole means you have 0.01 mole for every 1 liter.
Oh,
Which one has more in 1 liter?
and one.
1 mole. So it says in terms of aqueous ions, why is this guy a better conductor of electricity? The more ions you have, the more it is going to conduct the electricity. Because electricity is the movement of ions or electrons, depending on if you're talking about a solution or you're talking about a metal.
So I just say the 1.0 moles has more ions than 0.1.
That's the answer.
Okay.
Not that, is that what I should say? That is the answer.
Okay.
The 1.0 molar has more ions than the 0.01 molar.
Mm-hmm.
The higher the concentration, the more ions you have. Okay? All right, last minute question. Everybody good?
Yeah.
Do you have anything else you need me to go over? On Thursday morning, the day of your regents, on Thursday morning, I will be here for an hour. I am not teaching new material. That'll just stress you out. What I will do is I will say, right? I'm not going to say, okay, let's go over redox. I'm not going to do that. But if you say to me, I don't understand this redox question, we will go over it. So go home, do some practice regencies, and if there's any questions that you have about a specific question, email me, text me, or come to Thursday morning.
Wait, what time would Thursday morning be?
I don't remember. I think, hold on, let me just.